Okay, hello everybody. So right now we're going to talk about the derivative as a limit in formulas, namely this limit formula. And so let's take as an example this map. Let's say that f sends t to t squared t to the third. So we've seen this many times, this map. And, for example, so the input space is one-dimensional and the output space is three-dimensional. So I'll draw it a little bit. I remember this map, for example, it takes the point 0 to the point f of 0, which is 0, 0, 0, 0. It takes the point 1 and sends it to f of 1, which is 1, 1, 1, I guess. Maybe there. And then it takes the point, for example, 2, and it sends it to f of 2, which will be, a point in three-dimensional space. Well, what point? It'll be 2, I guess, 2, 4, 8. We plug in 2, 4, 8. So go 2, 4, and then, wow, I really need to go very, very high off the screen. And so we sort of remember this. It's a twisting up. It also, if we projected it down onto this first plane, we'd see that it's sort of a parabola. And it twists down below as well. Okay, so that's this curve. It takes this whole line to this whole curve. Okay, now let's calculate the derivative of this f at the point P in the direction V. So we're going to calculate it as a limit. And where we take P to be literally the point, well, let's say 2, and V to be the vector E1. So that means we're over here at the point 2, and we're going to move in the direction E1, and we'd like to know linearly, so f is this non-linear map, but linearly what will happen? And so we're going to actually move in some flat direction, not a curvy direction, but a flat direction. And we're going to see that now in this formula. Okay, so let's just rewrite the limit formula. So the limit as h goes to 0. So h is a real number. It's actually going to be our only variable. P will be 2, so this is not a variable. V is specifically the E1 vector, so it's not a variable. But h is going to sort of be our variable. And then we have f of p plus hv minus f of p. So that's the output change, it's a vector, and then we divide it by some real number, h. And now what's going to happen here is that, I'll sort of do it above, this piece, we're going to write it as h to the 0 times some stuff, plus h to the 1 times some stuff, plus h squared times some stuff, plus h to the third times some stuff, etc., etc., etc. So we're essentially going to, in the variable h, which is changing, it's going to go to 0, we're going to expand this piece, f of p plus hv, into the constant in h, linear in h, quadratic in h, cubic in h, and what's going to happen is only the linear piece will survive, because the derivative is a linear map. Now why? Well, what's going to happen is that f of p will cancel the constant piece. Then this h down here, this dividing by just the real number h, will come through and it'll cancel this h, make it into a 1. It'll cancel this h squared, make it into just an h. I'm just dividing by h. So h to the third becomes h squared, etc., etc. So now we've divided by h. So the subtraction here got rid of this constant term. The dividing by h change these h's a little bit, and then the limit, when h goes to 0, it'll send this entire piece to 0 and this entire piece to 0 because the h's are still around. But this linear h, when we divided, it became a 1. So when h goes to 0, this piece survives. And this is why the derivative is linear. Okay, so let's see that in this specific example with the map, this curve, this curvy curve in the plane. Okay, so let's see. So the limit of, I'm not going to bother writing stuff, f of p, well, p I said was 2, plus h, well, h is a variable. I'm going to let it go to 0 later. And v was e1. So this is a number times a vector. Of course, our input space is just a line. Later, we'll realize that maybe this is all taking place in the plane, and we could have moved in some other vector like e2. But for now, all we have is we're just a one-dimensional creature moving left and right. So really, we just have e1 or some multiple of e1. Okay, and then minus, now I said p was 2, right? P is 2, f of 2. Then I have to divide by h and the limit as h goes to 0. Okay, so let's keep going, the limit. And now f of 2 plus, well, e1, because we're in just one-dimensional space, e1, we'd think maybe it's 1 comma 0, but we're not even in two-dimensional space. So e1 is just like 1, and it's really just the number 1. It's just a movement in one unit, in one dimension. And so I just have an h. F of 2 over h, limit as h goes to 0. Now what happens? Well, the limit, let's plug in f of 2 plus h. So I take 2 plus h, and I plug it in to my map. What I get is a vector up here. This top will become a vector. What is it? It's 2 plus h squared. I'm going to write it as a column, 2 plus h to the third. There's my vector. F of 2 plus h is now this three-dimensional vector. Minus f of 2, well, what's f of 2? It's 2, 4, 8. 2, 4, 8. I still have to divide by h, so I have some vectors up in the numerator and just a number in the denominator, which I will let go to 0. Okay, so I can expand this. What I have is a 2 plus h. Then I have what? Okay. 4, let's see, 4 plus 2 times 2h plus h squared. Then here I have 2 to the third is 8. 8 plus 3, so I'm remembering my Pascal's triangle. And when I'm squaring, I needed that extra 2. When I'm cubing, I need the extra 3 here from Pascal's triangle. And 3 times 2h squared plus h to the third. So I expanded this out. And maybe I did it a bit quickly. You can pause and make sure that this makes sense to you. That is a vector. It has 1, 2, 3 components. Of course, they look rather complicated. But that's okay. They are what they are. So I'm subtracting 2 vectors and I'm dividing by some variable. And now let's do what I said we'd do. We're going to expand this part here in powers of h, okay? So what I'm going to do is I'm going to say, okay, well, first linear in h, all I have is the 2, 4, 8. So I'm going to write 2, 4, 8. Plus, so that was sort of like h to the 0. Now h to the 1, h to the 1 times what? Well, I have a 1 there. Here I have a 4h to the 1. Here I have a 2 squared is 4, 3 times 4 is 12. So I have a 12h to the 1. Now I have h squared times something. Okay, so there's no h squareds up there, so I have a 0. There's only 1 in the second dimension. And there are 3 times 2, 6 in the third dimension. So there's that h squared. Okay, and how about h to the third? Well, that appears none there, and once there. Okay, and actually that's it. I don't even have to keep going to h to the fourth plus blah, blah, blah. There's no more. I just have this subtracting. This was the minus f of p. And sure enough, like I said, the minus f of p will cancel the constant term. Because look down here, my minus 248, my f of p will cancel the constant term. Then I'll divide by h. And you'll see what happens. Then I will have to take the limit as h goes to 0. So what's going to happen is I'm going to have, well, let's do this here. So this h will come through and distribute to all the terms. These, of course, have already canceled. So what I'm going to have here is just a 1, 4, 12 left over times a 1, because h divided by h is 1. Plus h times 0, 1, 6, plus h squared times 0, 0, 1, and that's it. And no more divided by h. I already did that. I divided by h. That's why the h squared became an h, and the h to the third became an h squared. So now I've done with the divide by h. You see that I've canceled the f of p, that got rid of the constant term. Now I've divided by h, and that changed these h's a little bit. In particular, it changed this linear h to a 1. Finally, there's one last piece of the formula. The formula had many things, and the last piece is to take a limit. The limit as h goes to 0 means that this piece will go to 0 and this piece will go to 0 because they still have h's. And only the linear term remains. And so this limit is equal to the vector 1, 4, 12. Amazing. It's really fun to see that this works. This limit formula, the derivative of f at the point P, we're approximating the nonlinear map f near P in the direction of the vector v, where I took the vector e1, is this limit formula. And it gave 1, 4, 12. That is the derivative, or in this case, you could call it the velocity of this motion along the curve, if you want to just interpret it that way. But you're going to see this formula works in all dimensions. It's the same derivative every time. Okay, that's great. Now, what might I say more? Let's just look at this. If I had said, what's the derivative, and we had just blindly remembered single variable calculus, and we just take the derivative of each component, then a t becomes a 1, the t squared becomes a 2t, and the t to the third becomes a 3t squared. And then if we plug in t equals 2 at the point, t equals 2, then we would get, 1, 4, 2 squared is 4, 12. And that is, in fact, exactly what we got from our limit calculation. So good. It is working as we would hope, as we would expect. Okay. And remember, when we take in calculus, we sent x to x squared. Like, why is the derivative 2x? When we send x to the third, why is the derivative 3x squared? Why? And actually, if you'll remember, it's this limit formula. We had a f of x plus h minus f of x over h, and limit as h goes to 0. And x plus h to the third is then going to be x to the third plus 3x squared h plus 3x h squared plus h to the third minus f of x is just minus x to the third divide by h, and you see that the constant terms cancel. This h becomes a 1, and these h's will stick around, so finally in the limit, only this piece will remain, but the h has become a 1, and so then we get 3x squared. And so you see sort of, this is why. The great thing is from single variable calculus to multivariable calculus is that it is identical, the formula. The only change is that, this was secretly an E1 vector, but now we're just going to actually put the vector there, HV. We're moving the amount h in the direction v. We're moving the amount h in the direction v. When v is equal to E1, like it was here, then E1 is just like the number 1 in one dimension. And so that's why we get the old single variable calculus limit definition. Okay, thanks everybody. So now you understand why the derivative is linear. It's because in this formula, the constant term cancels. The division by h turns only the linear one to a 1. Everything else has an h remaining, so when the limit of h goes to 0, the linear term is the only remaining standing piece.